Tom, do you have the slides, or do you want me to,
I do.
share? And
I have
okay,
the
why don't
slides
you
just
try?
in another, let's see, where'd my mouse go? That's the only, there we go.
So you
And
can
then
share
menus, you
your
can certainly make,
screen, and
oh
you
no,
can
that's the
control
wrong
the
button. I can
slides.
share the, how do I share the screen?
There's a button in the lower part of the web
A green
interface that
button
says
there.
Share Screen in green. Yeah.
Oh,
This is
green.
Tom Clooney, everybody. Tom's a research scientist at Goddard Space Flight Center. He's the one who graciously rewrote our calendar to do all kinds of fun stuff, and you'll hear him talk about that now.
Okay, I probably should
Thanks,
do
Tom.
something to make this full screen too. Let's see, view full screen.
And you click on present on the top right.
Okay.
And then there you go.
Ah, there we go.
There we go. Perfect.
All right, and I'm all set. So thank you, Mike. So let's jump right into it. So when we say calendar, there's several different things that are tied together here. The basic idea is that there's some internal representation of time on the model's part that needs to be connected between the orbit and the various angles that are associated with the orbit and the distance from the sun and such, as well as some sort of calendar for us to be able to meaningfully understand time. I mean, giving us, absolute time in seconds doesn't really help us figure out whether it's winter, summer, how many years have passed, that kind of thing. So the calendar basically translates the model time into our notions of year, month, day of year, hour, seconds. All sounds really good, right? So there's lots of ways we can do that. Oh, and I didn't shift this right yesterday. I apologize. I was trying to lift. So pardon, those lines in the middle diagram actually did end at the ellipse until I shifted those yesterday. Anyways, so the basic idea that we try to do is we try to keep the angles that we associate with our calendar to correspond with the angles that we associate with the Earth in the regular calendar. In particular, we divide the solar day on a planet into 24 equal hours. So this is a little bit different than some of the other calendaring systems out there do. Rather than keeping the notion of an hour as a fixed number of 3,600 seconds, we actually keep 24 hours in a day and let the hour be whatever it has to be to make that happen. Then for the seasons, what we do is we divide up the orbit into 12 angles, each of which subtends the same angle as the corresponding month of the Earth around the sun. So February will tend to be a shorter month, and July will tend to be a longer month just because that's the way it works on the Earth. But it does get modified then by the properties of the ellipse. So a highly elliptical orbit that just happened to be at apogee in February could end up having February be a relatively long month, but generally speaking, it works out for the way we want. One other thing we do is we want the number of days in a year to be an integer number. Even the Model E, when it's running for the Earth, we don't include leap years. They're not that important for climate purposes, and it makes a lot of the bookkeeping easier. So what we do is we actually adjust the period slightly in order to make those commensurate. And when you get to more extreme orbits, you might find that a little bit annoying. For ordinary orbits, that's not usually much of a deal. Okay, so the problem with this approach is when you go to the extreme orbits. We usually make the assumption that the angular frequency of the planet around the sun is much, much less than the angular rotational frequency of the planet about its own axis. When that happens, then we can make this approximation that there's an integral number of solar days per year, and that we can divide it into 12 roughly equal months, each of which has lots of days. And when you get something really slow, especially a tidally locked planet, these assumptions go out the window, and you can't really end up with a calendar that's much like what you and I are used to. So what do? What we do is when the orbit's slow enough, when the rotation is slow enough, we separate the connection between a calendar day and a solar day. So whenever I refer to solar day, I'm going to refer to the time it takes to go from noon to noon on the planet. So the calendar days end up being a fiction once we get down to that point. And in fact, we make it so there's always 120 calendar days, or at least 120 calendar days in the year, so that we can still have 12 months, each of which has roughly 10 days, so that days for averaging purposes and such are still somewhat useful. But at some point, you do have to start being wary about diurnal diagnostics. You could have, for a slow enough rotator, monthly averages can be very misleading. You can have more daylight in a month. You could have an entire month of daylight, even at the equator in extreme cases. When you get to extremely slow rotators like Venus, we also have to break this assumption that I mentioned on the earlier slide that the number of days per year is quantized. Venus has a day that's about 1.5 years, if I remember correctly. You might correct me on the details. But when you get down there, if you don't include that effect, then you don't get the right dynamics. But what that means is you sort of have to, in calendar years, no longer correspond to actual sidereal years of the orbit, and you need to think about that. If you need to average over a year, what you probably have to do is run enough years that you get an integral number of both calendar years and orbital years, so that you're not putting any bias from either one of those two things going on. Okay, so what are the run deck parameters to set all this up? So the first thing is, if you're running anything in Model E and you want to do anything other than the default Earth orbit, you need to set the planet name to be something other than Earth. If you know the name of your planet, for like the Mars and such, then you can do that. Otherwise, you can make up a name, or some people just put not Earth. That just triggers it to unlock things so that you can set things away from their defaults. The next few are sort of obvious terms from the orbital mechanics. You can change the obliquity of the planet. You specify it in degrees, the eccentricity, and then the longitude of periapsis, again in degrees. And again, for all of these, if you don't do anything, but you have changed the planet name, you'll still get the default for modern Earth. Okay, so you need to be, you can't just say, oh, it's going to be 0 if I don't set it. You need to actually explicitly do this. You probably want to set it for all of them, just to indicate that you thought about it. And then there's a sidereal orbital period. This is in seconds. And the sidereal rotation period, this is seconds. Now be careful, this is not the time of the day. This is the time it takes the planet to rotate around once. For the Earth, this is actually more like 23 hours and 56 minutes. Okay. Then there's an option which we force you to set because it was getting confusing when nobody did. This is the quantized year length. Most of the time, you're going to want to set this to true. But again, if you get down to an orbit that is extremely slow, a rotation that is extremely slow, like Venus, then you want to be able to set it to false. But you probably also want to talk to somebody, make sure you understand some of the implications when you relax that constraint. And then a very recently introduced parameter is to control the equation of time. Some of you may have noticed on your toy globes as a child that there was this sort of figure 8 that was usually drawn somewhere over the Pacific Ocean that was labeled with different colors for the different months. And what this was basically telling you is where noon is relative to the clock noon as the year progresses. And this has to do with the fact that two things. One, because the Earth has an elliptical orbit, the effective rate at which the sun goes across the sky is actually a little bit faster in the winter when we're near periapsis, and a little bit slower when we're near apogee. Sorry, I'm not using consistent terminology there, but you know what I mean. And it's also somewhat affected by obliquity, but primarily eccentricity in the case of the Earth. But we've, in more extreme places, like Mike studied a planet which had a 3-2 resonance, not quite tidally locked, well, tidally locked, but not in the 1-1 resonance. This can be a significant effect, and so we had to add that back in. The first time we put it back in, we didn't include the effects of obliquity. Mike was studying zero obliquity, and I didn't even think about doing the three-dimensional geometry. And so we have, for historical reasons, we have something called naive as an option there, which gets you the eccentricity effect for the equation of time, but does not give you the obliquity effect. We recently added in the obliquity correction. So on either the planet or the planet 1.0 branch, if you want the equation of time, you should turn it on. It's never wrong. We leave off as a default on some of the branches just so that for Model E Earth, you get the same correspondence. For the Earth, they don't have the equation of time. Someday maybe they'll accept it, and then we can get rid of the off option completely. But for now, we have the on, which is probably what you want. And we have the naive if you want backward compatibility on the 1.0. Otherwise, you probably don't want naive, and you probably don't want off. Okay. And then there's a few other rarely used parameters. One is mean distance. Model E has two different ways to control the illumination of the sun on the Earth. One is, I forget the name of the parameter. I want to say it's like SOX, S0X, something like this. Mike, you want to chime in on that one? But you can also
it's _S0, yeah.
Okay, and you can also, but you could also just change the distance of the planet. So if you take all the Earth parameters and change mean distance to 2, then you will have cut down the illumination on the Earth by a factor of 4. Likewise, if you don't want your if you don't want the high noon to be, or actually midnight in this case, directly over Greenwich on your planet, if for some reason the longitude of your planet actually has a meaning to you, then you can adjust that with the hour angle offset, and this is in degrees. Getting the sign right, you might want to double check things because it's not entirely obvious which direction that goes for you. Okay, and that's it for orbits. I went probably a little bit fast. Are there questions?
I just want to mention quickly the hour angle offset. The reason we put that in is for tidally locked worlds where you have topography. So let's say you take Earth's topography and you put it in a tidally locked system, and you would like the substellar point to not be over the Pacific, which is the default. If you just put it in and you want it to be over Africa, you can change this hour angle offset so that the planet's substellar point is sitting over Africa. That's what this is useful for. And you'll see that in our Proxima Centauri B paper. We have 2 tidally locked simulations with Earth topography, and one is with the substellar point over the Pacific, and another is with the substellar point sitting over Africa.
Okay.
Excellent.
In practice, if you have an unusual situation, feel free to contact me. Usually it takes me about 10 minutes to put my Model E orbit hat back on and remember how it all worked, but usually we can resolve issues very quickly.
Absolutely. Tom's really good at this stuff.
Okay.
Great. Thank you, Tom. Thanks for dialing in.
No problem. Take care. Enjoy.
All right. Okay, our next slide is going to be boundary condition files, which I think we already talked about quite extensively yesterday. I'm not sure it's worthwhile to go through this again. So I think we should move on to the next slide, 51, and Igor will tell us about the Mars run deck and the various parameters involved there. And having just heard what Tom was saying about some of this should ring true to you. So Igor, can you take over and share your slides?
Yeah, I'll try to share it.
Excellent.
Let me just adjust it. Oops. Second. Yeah. Okay. Can you see it?
Yep.
Yeah.
Looks good.
Okay. Okay. So I'll be talking about Mars and basically together with land hydrology stuff, because Mars is a land planet, so it's convenient to discuss both in that in that respect. So basically, just to continue what Tom was describing, the first thing you do basically when you create a Mars run deck, you have to specify different orbital parameters. So this section just shows you what basically you have to do. We have already seen this parts in the run deck yesterday, but here's again. So you specify the name of the run deck, which will be used inside the planet params module in the source code to specify other stuff for Mars. I mean, surface pressure, atmospheric components, and what else? Yes, gravity. So then here you specify eccentricity, obliquity, longitude of periapsis, orbital period, rotation period, and we set quaternions year to true to have an integer number of days. So that's basically it, I guess, about this part of the run deck. So roughly the year is twice longer than Earth year, and that's if you don't know, that's basically what you observe on Mars. And here's extraction from PRT file. When you start the model, you could try to do a test run really quickly with Mars run deck, and that's what you will see in PRT file at the beginning. So those are orbital parameters that basically are computed or like reproduced from the run deck for your reference. That's what's going on. Like how long is mean solar day? You see that it's pretty close to Earth day, just slightly longer than rotation period, orbital period, just shown for your reference. So that's pretty much about this slide. And if you go further into PRT file, just for you, again, for your reference, it basically shows you the calendar. So you can see that each month is roughly twice longer than on Earth. So these are the days of the month, and then it shows you nice statistics about basically what you want to know about your year. It's apsis and periapsis, where your planet is closest or to the star, or vice versa. Vernal equinox, summer solstice, winter solstice, and autumn equinox. So these are things nice to know when you start the model. You should look at these numbers when you create new calendar, just to make sure that it's something meaningful. One thing for Mars to notice that periapsis happens basically in the winter, in the northern winter, so that northern winter is warmer than southern winter. That's the thing to remember. Now I want to show you just the Mars topography once again, because yesterday actually I have shown you lunar topography for some reason, because I had two on my screen and I showed the wrong one. So this the topography which you set in the run deck. You have already seen which file you will be using. One thing just to notice here that Mars has lower topography in the northern hemisphere than in southern hemisphere, and that will also have effect on the pressure curve, which I will just show in a minute. So this is the pressure curve, which also Mike showed you. Here's again. So basically, what I have shown you in previous slides about Mars setup, that all it takes to get this curve, it basically doesn't need any additional additional tuning to just get roughly this pressure curve. It's pressure at Viking landing site, and the pressure changes because your atmosphere condenses either on northern or southern pole, depending on which time of the year you are in. And thinking is, of course, there are two spikes during the seasonal period, because you have northern winter here and southern northern winter here, yes, and southern winter here, because of non-zero obliquity. And one thing to notice that the spikes have different amplitude, and that's because of two things. Because you have non-zero eccentricity, so southern winter is warmer than northern winter, and also topography is lower in northern hemisphere. That also helps to northern winter to be warmer because of greenhouse effect. So that's about this slide. And then one thing I wanted to show you, we already discussed how you set up the topography, and here how you set your albedo in the for the planet. The way to set it up, it's a little weird because it basically was inherited from how it was done for Earth. And for Earth, you use vegetation file, which is called veg, where you specify all land cover fractions. So you specify there are all vegetation types, and you also specify the fractions of bare soil. For Mars, of course, you have no vegetation, but you still have two types of bare soil, which we call bright bare soil and dark bare soil. And that's what, that's just the way basically to describe your albedo. So weighted average of those soils, one has albedo 0.5, other has albedo 0, that will give you ground albedo. So that's basically what is defined right now in Mars veg file, two types of soil, and together they give you ground albedo. And at the bottom here, I show you ground albedo for the month March as it appears in our model after you run it for a few Mars years to the equilibrium. So you see two things here. You see all the features of albedo that you defined in your input file. So that's basically just reproduces your input file. And at the north, you see much brighter albedo. That's because you have CO2 condensation here. So you create a polar cap during the northern winter, and that basically changes your albedo. And so far in our model, we just use the albedo of CO2 snow is the same as albedo of water snow. So that's something that will change in the future generation of the model, but so far it wasn't tuned well, but you still have seen that it gives you pretty good pressure cycle anyway. So that's all what I wanted to say about Mars, and now I'm switching to more general description of ground hydrology. So Mars,
hold on, Igor. Let's see if there's any questions about those slides first. Does anybody have any more questions about the Mars stuff? I see one in the chat window from Stephen.
I have one about the CO2 albedo. Is that possible to change it? It's a constant value, or could it change with time, for instance?
For CO2 albedo, we use the same algorithm which is used for water albedo. So as far as I remember, I did it properly, probably, as I think I used I initialized water albedo. So mostly it just changes with time as the snow ages. So if you don't have any new condensation, basically like during the fall, you always have new condensation, so you always reset your albedo. It's always the brightest. But once you get to the spring, you don't condense CO2 anymore. You just start to sublime it, and the snow becomes older, so it becomes darker. And the equation which is used, like dependence on the age of snow, is the same as dependence for water snow, which is of course not quite correct for Mars, but we didn't have anything better. So that's just a hack basically to get things working. But yes, that will change pretty soon. Maybe not in Planet 2, but definitely in Planet 3 we will have proper CO2 albedo. So yeah, and of course it changes seasonally because the extent of CO2 condensate changes. So if you just run the Mars model and look at there is a diagnostic for CO2 condensate on the surface, you'll see how it changes seasonally.
And of course, the dust tuning in the model would affect the albedo over time also.
Yes, it should, but it's not in the model yet, I think, because we
Well,
have,
You're correct. We're working on
yeah.
that. Right, Kostas?
yeah, so the dust thing is, it will change the
Yeah.
albedo if we take into account migration of dust from one location.
Yeah.
And this is something that we have proposed to do, and we are, but yeah, we have not started working on that yet.
Yes. The water algorithm, the algorithm for water snow has black carbon in it, but unfortunately there is no black carbon on Mars. But in theory, yes, if you hack the model and just substitute dust for black carbon, you will get something. But yeah, that's still, no, this is still a research project, so, and that will hopefully will be done pretty soon. So yeah, that's basically how people tune this, tune their models so that they get perfect match between Viking data and modeled data. So we didn't do it here, so you see basically that it's different because on different poles you have different amount of dust accumulated. So usually people tune southern pole and northern pole separately, and then you get perfect match. But we didn't do this, so that's basically what model gets you without any tuning. Any more questions on Mars? I guess we can discuss it at the end of the day if somebody still has some questions.
Yes,
So that's,
I agree. Thanks, Igor.
yeah, so I'm switching to a brief description of ground hydrology. And so this is a paper, original paper. Yeah, there's two papers where basically ground hydrology is described. So 97 is original paper if you want to see what it actually is. So I will have no time to describe everything in detail. So this complicated plot is just shown basically to sort of impress you, to see that, to show that it's not a trivial bucket model, but there are a lot of things here. Those are all these arrows are different fluxes, and all subdivisions here are different fractions of surface, and also snow and CO2 condensate were even not put on this plot, so they also complicate picture. So basically, roughly what you have, we have 6 layers of soil in this model, and it's those are different. They have different prognostic variables for vegetated soil and bare soil. Vegetation can be wet and dry, and that also changes fluxes. Then you have snow, which you may have like on bare soil. You may have snow under vegetation, and you may have snow on top of vegetation, and that all has different fluxes. So the basic fluxes are sensible heat, which is due to basically temperature changes between surface temperature and ground temperature. You have latent heat flux due to evaporation. You have incoming short wave radiation, incoming long wave radiation. You have emitted long wave radiation, which is different for each surface type. So it's different for vegetation, it's different for snow, it's different for bare soil, and snow under the canopy and ground under the canopy exchange heat fluxes between canopy and ground, and sensible heat flux can penetrate from under the vegetation and still go out, and fluxes from ground under the canopy depend on leaf-area index. So if you're in summer, then your canopy has 10 leaf-area index, basically nothing penetrates, and in winter leaf-area index is low, so you get fluxes out. But there are still also some limitations, like how radiation is computed. So radiation, basically, for radiation, canopy is still considered to be impermeable. So you exchange radiation with canopy, and then canopy exchanges radiation with the atmosphere. And I guess I didn't describe this global input. So basically, globally, what you have first layer of atmosphere, which is represented here. Then you have surface layer of atmosphere. Surface layer is lower 10 meters of atmosphere. So these values are computed by planetary boundary layer module in the model. And then these values are used basically to compute all the exchange with canopy and land surface. And snow has 3 layers of snow, also not just simple bucket model, but real snow. Can change thickness and can change density depending on how old it is. It can compact. The water can melt and refreeze in lower layers. So that's also modeled properly in the snow. And snow has snow fraction, so it can have different extent depending on how much basically snow you have, and it also depends on your topography. So rougher topography has lower fraction of snow because soil can stick out. Yeah, and the total thickness of soil is 3.5 meters that you want to know, and you may want to change it for different planets because basically that was tuned for Earth's orbit around the sun, so that basically it kind of represents seasonal cycle. So for slower planet for longer orbital cycle, you may need thicker soil. And what else? Describe. Yeah, well, if you would want to talk about water equilibrium, you have to know that all this stuff has to get into equilibrium in your model when you do your runs, because usually you initialize your model with non-equilibrium state, and depending how you set up your model, you may get to equilibriums quicker or slower. So basically, for example, the underground runoff from the soil depends on the local slope of your topography. So if you set it to 0, then there is basically no underground runoff. Water stays in the soil, but it can still evaporate from there, taken out by capillary forces, but those are very slow. So it may take thousands of years for your model to get to equilibrium. So usually it's a good idea, even though you think that your planet is pretty flat or you don't know what topography it is, still to set non-zero slope so that your water will be draining from soil reasonably fast, and it will go to the lakes, and that will help your to get equilibrium quicker. And let's see, yeah, probably, yeah. And I think I should mention the lakes briefly. So lakes algorithm by default is also has dynamic lakes, though you can switch to static lakes if you really want to. You defined lake fractions in your topo file. You can look at it. There is a fraction there, but if you have dynamic lakes, that's just the initial condition. It will be changing, and the lakes I assume to have conical shape, so the refraction changes depending on the amount of water in the lakes. And if you don't define the shape, then by default, basically the slope of the lakes will be 2000. It's ratio between height of the lake and its radius. They can change to cylinder shape when they become very thin, but I think it will be, this algorithm will be submitted on Planet 2, so it's not yet there. Yes, and they of course can evaporate completely if you don't have enough water for them. So it's probably all for this slide. I wanted to say. So here what we have is just a couple of notions. Basically just here it's a rough formula of how lakes is formed. So it's formed from soil runoff and precipitation, and evaporation takes water, and also we have water transport between the lakes and different cells and GCM cells, and that is defined by your topography and by river directions files. I don't have time to go into the details, but you have to specify that file if you want water transport between the lakes in your model. You can still skip it, and then there will be just no water transport between the cells. So the lakes will still form, but they will be kind of local lakes. So they will form or evaporate locally. Okay, and here just this basically two formulas just briefly mention what kind of water you have in the model. If you don't have ocean, I'm talking about land planets, so it's basically just atmospheric water, which includes just vapor and clouds, and on the ground you have snow, you have water in the ground, and you have water in the lakes. Water in the ground also basically water on the canopy also kind of implicitly assumed that it's here. And if you want to talk about available water, which usually people who deal with plants like to think, then you should remember that part of the water is frozen and part of the water in the soil is actually bound so tightly with capillary forces that you actually cannot extract it. So it's there, but basically plants cannot take that. So it's always there. So you have to subtract it if you want to know how much water you can get from the plants. So now I want just to briefly discuss the input. So basically, all I was describing is like for ground hydrology, those are the input files which you are using in your run deck. These are basically this is just some minimum that you usually should have in your run deck. We already have seen, I think most of them in some example run decks, but I just want to mention it again. So veg file describes basically the fractions of soils, and it's used to describe your vegetation, or if there is no vegetation, you still need it to describe albedo. Top index file needed to describe standard deviation of topography that is used for computing of snow fraction. And also, if you don't specify roughness length, that will be used to automatically to compute the roughness length. Then soil file specifies soil textures and local slope. Then roughness length, you can specify it directly, or if you, as I said, if you don't specify it, it will be computed from standard deviation of topography that you specify. And soil IC, it's initial conditions for ground hydrology. This is basically just temperature of layers, water content, and an amount of snow. And I don't have time to go through all those files, but we can look at them during the discussion section if there is an interest. I'll just show as an example just one of these files. So this is soil file, because people asked yesterday, so just wanted to show. So basically the way to look at it, you just go to directory with input files and just do nc dump and on that file. And at the beginning of the dump, you will see all the structure of file if you are not familiar with netcdf. And I just put comments here. Unfortunately, currently most of the files are not documented well, so you don't see these comments. I put them in red just to basically explain you what it is. So it includes, of course, a resolution of the model. Then NGM is the number of layers in ground hydrology, it's 6. And IMT is the number of textures. So it's soil, sand, silt, clay, peat, and rock. And you specify textures for all of them. And this is data fields. So you specify soil layer thickness for each, basically for each column and for each layer. Though usually they're set like constant, set uniformly over the entire globe, but they could be different. That has not been tested for many years, but I don't see why it shouldn't work. Just you didn't need to define it separately for different columns. But most importantly, so you usually leave it just as it is, but most importantly, you specify soil textures in fractions. Those are traditionally specified differently for the centers of the layers, and for the edges of the layers, they're usually the same numbers. And you specify local slope, and I write here specifically that's a typical slope. It's not average slope. You don't want to take it just from a low resolution topography and say, well, it's nearly flat. You actually have to think in terms of scale of like tens or hundreds of meters, how it should look like. And so it's usually higher slope than it will be average slope. So you have to put it in that way. I mean, it's like local slope, and you may want to tune it to get proper underground runoff because you typically don't want to have it basically to have zero underground runoff. And that's pretty much all I wanted to say about ground hydrology. There is a lot of stuff there, because if you have questions, but maybe you should postpone it to discussion section if people want to discuss.
Yeah, because we should take a break.
Yeah,
we should take a break now. And,
yeah, because maybe we will be discussing how to create a planet, and maybe that will be also partially discussed there. So after we like look through all the information, maybe it will be like easier to understand, or the questions are more obvious.
Yeah. So let's take we have like I said, originally scheduled 15-minute breaks. Let's take a 12-minute break. We start back on the hour, and then Kostas will quickly review what we mean by equilibrium, show you a few plots, and then Eric Wolf will talk about the radiation, and then we'll move on. Okay, so we'll take a small break and save up your questions for the Q&A this afternoon. Thank you, Igor.